Everybody, hi everyone. Thank you for being here. So this is session 14 of ITCS 2022. As the tradition of ITCS, the session chair will give, I'm going to give a very short, brief overview of the talks of this session. So we have 5 talks. I want to give every speaker 10 minutes. Okay, so I'm just going to take like a few minutes of your time to give some overview and make sure everybody is intrigued for the session and stays to the end. Okay, and so let me close this. Okay, so usually there's this search of a unifying thing for the session. Sometimes it's quite hard because the papers are different. So here I'm going to something broad, okay, about all these papers are about doing the impossible. Okay, and of course they're not actually doing the impossible, but you know, as I read them, this is what I feel, and I can show off the paper more than the authors themselves. Okay, so this is what I'm going to do. So the first talk, so this is on the download rate of homomorphic secret sharing, and like in one sentence, what they do is they're gonna do secret sharing with less than 1 bit. Okay, so that's really doing the impossible. And how do they do that? Well, okay, it's not really less than 1 bit. There's some amortized thing of the download rate. But really, first time you read the paper, you're like, oh, no, you cannot do better. And then they're like, oh, you actually can you do better when you amortize things. And so this is really a paper about, you think you know everything about Shamir secret sharing. And you know, every day it's quite amazing that we can still get more out of this. The second paper in this session is small box cryptography. So what they do is in this paper, they consider the AES encryption scheme, and they prove that it is secure. Okay, so this is completely impossible, of course, at least without like proving that P is different than NP. But really, reading the paper, you just get the feeling that it's almost there. Okay, they have a very nice proof of how they start to break this AES box to small and small parts, and they get to something they call the small box, and it's very, very nice. It's like really almost a proof of AES. The third talk is on average hardness of NP, and this is like, you know, in the realm of theory, this is like one of the most interesting open problems, right? So how do we get from the worst case hardness of NP to an average case hardness of NP? Actually, Amnon Tashman has a very nice paper showing that if P is different than NP, okay, then where are these hard instances? You can actually find them, okay? They're not actually too hard to find, so you can sample them, but the running time of this distribution is not polynomial, it's only quasi-polynomial. And this is really not what we want. We want like a real polynomial time distribution, you know, that fools any higher polynomial adversaries. So this is one step in that direction. Okay, of course, they don't completely resolve this question, but it's really a nice step. And I don't know, all these steps really make me optimistic that we might solve this question in the next 10 or 100 years. Okay, the next paper is, well, the title itself is already something that's impossible to do. So they're beating the classical impossibility and opposition verification. I would say they're breaking the speed of light. Okay, so I want to know that somebody is near me. So I'm going to tell him, okay, just I'll send him a ping and he has to respond, and I can time this. And I know that if, you know, by the speed of light, if he answers very quickly, I know that he has to be nearby. And then you can do many of these things, but it's quite amazing what provers can fool you, okay, in this setting. And here they give a very nice solution with quantum provers. Okay, so stay tuned for that. I think this is a very cool paper. And the last paper, so this is on IO and this indistinguishability of obfuscation. But the thing they're doing that is possible is really using 0 circuits, okay, to beat quantum adversaries. So why are 0 circuits so powerful? These are like a circuit that always output 0. Okay, this is like the useless thing in history. And this really helps. Okay, of course, this is a obfuscation of 0 circuits. But this is very tight. So actually, they do two impossible things. They build I/O, and then they show how from this I/O that they build, it's actually very powerful. Yeah, so I really also like this paper. So I think we have a very great session. And with that, let's see what's the time. Yeah, with that, we'll start with our first speaker. So this is going to be Victor, right? Okay, great.
Right. So can you hear me?
Yeah, we can hear you. Victor, the stage is yours. Please introduce the co-authors.
Hi, so I'm Victor Kolobov. Thanks for having me. This is a joint work with Ingerid, Fosli, Yuval, Ishai, and Mary Wootters. And today I'll talk to you about the download rate of homomorphic secret sharing. So consider the following application of FHE. Alice has some input, and she wants to delegate the computation of some function on that input, such that then Bob can recover the evaluation of the function on the input. So what FHE gives us, first, it allows us the scheme to be such that the server cannot learn Alice's secret input. And also the work Bob needs to do to recover the value can be significantly smaller than the complexity of the function being evaluated. Now, homomorphic secret sharing, or HSS for short, can be viewed as a distributed variant of FHE, where instead of encryption, we are doing secret sharing. And here, T-privacy in this talk just means that any collusion of T servers or less cannot recover the secret input. Now, the downside of HSS compared to FHE is that we need to assume that there are multiple non-colluding servers, but for many applications, this is not an issue. And on the flip side, we can get various efficiency features such as editable construction. We don't need to worry about keys. And also, unlike an encryption scheme, secret sharing and HSS can exist with information theoretic security, for example, for simple functions. So why are computations on secret shared data useful? So one scenario could be that the clients have some input and they want to learn some statistical information which depends on all of their inputs collectively. Another application is private information retrieval, which is a well-known primitive, where the client wants to recover in a private manner some record from a database, from the database which is replicated between some servers. And indeed, in both of these applications and in many others, we care about large-scale computations on secret shared inputs. So here, large scale means either the record size is large, or in the first example, there are many statistical functions we want to compute. So the primary goal of this work is to try and minimize the download cost for the client. So looking for HSS for degree polynomials, how can we construct such schemes? For example, we can use Shamir's secret sharing. And indeed, in this case, the download rate for the client is 1 over the number of servers, where download rate just means that the amount of information we want divided by the total amount of information we download is the download rate. Now, can we do better than 1 over the number of servers? The answer is yes. We can use the so-called packed Shamir, where instead of encoding in Shamir one secret value, we encode more than one secret value. But then the download rate for degree polynomials approaches 1 over d as the number of servers grows. And this begs the question, can we approach rate 1 in some manner? So in this work, one way we show how to solve it is to use the so-called universality of CNF secret sharing, which was introduced by Kramer, Dankert, and Ishai from 2005. And the approach to do it is to first start from some T-private CNF sharing of the inputs. Then it is not difficult to see that this can be converted to a TD private CNF sharing of the outputs, where the outputs are just the polynomial evaluations from the secret inputs. And using the universality of CNF, we can convert the CNF sharing to any linear secret sharing. In particular, we can consider a joint linear secret sharing with high rate. And this gives us our HSS scheme. But then the downside of this simple approach is that the upload cost has a term which goes like the number of servers choose the security threshold. But what comes to the rescue is regenerating Reed-Solomon codes. And we cannot use off-the-shelf regenerating Reed-Solomon codes, but we can adapt ideas from this literature. And this gives us a scheme with Shamir secret sharing input shares instead of CNF input shares. And then this term becomes just roughly the number of servers minus the security threshold. Moving on to our results, in the first part of our result, we obtain an optimal download linear HSS for low-degree polynomials. Here, linear just means that both the share and reconstruction algorithms are linear functions. And optimal download means that we obtain both a positive and negative result. So indeed, for T-private K-server HSS for degree D polynomials, we obtain rate 1 minus dt over k, and one application of this is for information theoretic T-private K-server PIR for n-size databases with polynomial upload cost and download rate, which is, as you can see in the slide. This can be compared to the optimal rate for PIR without upload cost restriction, which is 1 minus t over k divided by 1 minus t over k to the power of n. And even for small database sizes, this optimal download rate is roughly 1 minus t over k. So we sort of reach the optimal, we approach the optimal download rate. A second part of our result is a black box rate amplification technique for HSS with additive reconstruction. In this talk, I won't show you the black box rate amplification techniques themselves, but I can just give you some corollaries that we can obtain from this approach. So for example, we can obtain a T-private K-server HSS for circuits from LWE with a high download rate. We can also obtain a one-private K-server PIR from the minimal cryptographic assumption of one-way functions. Of course, with small upload cost. And this is compared to previous high-rate PIR constructions from LWE or DDH, where on the flip side, they have they require only one server, but there the record length L needs to grow like a polynomial in the security parameter, while our result gives a sort of a different flavor because the record length can just be the number of servers minus 1, and it is independent of the security parameter. Furthermore, we can obtain a one private K server HSS for branching programs from DDH or DCR with high rate. And going back to information theoretic security, we can obtain a PIR scheme with subpolynomial upload cost and rate which approaches 1 as the number of servers grows to infinity. Now, finally, in the third part of our results, we obtain a nonlinear rate amplification technique for HSS. So what unifies the previous two types of results is that we need to increase the number of servers to increase the download rate. And this begs the question, can we somehow increase the download rate without increasing the number of servers? So the main observation here is that the output shares are non-uniform and correlated, so we can draw inspiration from distributed source coding. Unfortunately, the well-known Slepian-Wolf coding result does not apply here syntactically because of the privacy requirement of HSS. The servers don't know the distribution. Nevertheless, we are able to obtain a Slepian-Wolf style result for HSS with nonlinear reconstruction and negligible error probability, and applying it to a one private free server HSS for the end of 2 bits, we're able to beat the 1/3 rate. And this HSS can be useful, for example, for applications such as private set intersection. So this is all, and thank you.
Okay, thank you, Victor. Thank you very much. We do have a minute for questions. So if there's any question from the audience or panelists, you can raise your hand. Okay. You can also just unmute yourself if you have a question. Okay, so we're just gonna move to the next talk. So this is small box cryptography. Harish, are you giving the talk?
Yes, I am.
Okay, so you can share your screen.
Sure. You're able to see my screen, right?
Yes, we see it great.
Perfect, thank you. Thanks for the introduction. This is the talk about small box cryptography. This is joint work with Yevgeniy Dodis over at NYU and Daniel Wichs at Northeastern University and NTT Research. Sorry. So the question that we begin with is, what is the biggest open problem in cryptography? Now, obviously, there's no one right answer, but a possible candidate, which is also the motivating application for our research, is the provable security of AES. And the reason being, it's used everywhere and every day. Now, with that being said, what is AES? And if you actually take a minute to write it down, it looks a bit messy. It looks like a chicken scribble meets a doctor's note. But we theoreticians love a good abstraction, and we have done just that. And we have sort of taken the essence of AES and abstracted it out to something known as a substitution permutation network. So an SPN essentially is a sequence of structured rounds where you have, you can see the figure over here, where you basically have these three operations: a key addition, a substitution, and a permutation. And the point here is that the S box is the only nonlinear piece here. And why is it interesting is also because a lot of other ciphers have also gone on to use the same design. So considering how heavily it is used and how heavily it has inspired a whole series of ciphers, the question we ask now is, can we prove security? And the thing is, we cannot prove it unconditionally, at least not without proving P versus NP and taking home $1 million. And there are some results, however, which are interesting, but in a very restricted type of attacks. In this work, we ask is, can we be a little more ambitious? Can we prove it from either using an idealized model or some assumption? But then we hit a roadblock, and the reason is that this S box by design is very small because you want the process to be efficient and so on. And it is the only source of hardness. Now, and so it's unclear how to exactly do it, where sort of this S box and combining this S box, which is small, with an idealized model or an assumption. And recall that also an SPN is a series of structured rounds, and there is not a lot of theory on how to iterate something so small, such as an SPN, for many rounds and get reasonable result, at least not until this work. So this is the setting. Now let me sell our remedy or tool, and we call this small box cryptography. It is a mixture of proofs and hardness conjectures, and the former is liked by us theoreticians, and the latter seems to be necessary unless, once again, we solve P versus NP. And it basically consists of 3 steps, the framework, and it could be applied to a lot of things. We do it for an SPN AES setting, and we also do it for a PRG or a stream cipher. And there are 3, the first step is basically a traditional reduced round proof, where we prove it either for 1 round, or in the case of an SPN, we do it for 3 rounds. The second step is sort of this hardness amplification, and this could possibly be provable. And in the case of SPN, it is provable if we know the key schedule. And the third step, which is the conjecture part, is the big to small conjecture. And the way to think of it is almost the one-way function equivalent of this new branch of cryptography called small box cryptography. And why is it, I mean, considering there's a conjecture, why is it of some interest, so to speak, is because at the end of the day, what we come up with is something that is almost a real AES, and there is no unspecified big components. And it basically explains existing constructions and hopefully will guide new designs. And we derive precise quantitative bounds where there's an explicit dependence on the number of rounds. And the results we get is strong, but certainly more conservative than some of the real world choices anyway. So what do we get when we apply the small box cryptography framework to our SPN? So let me tell you how it works. Using the most aggressive big to small conjecture, we get the following security that we get for an 8-bit S box, we get security, which is epsilon equals 2 to the negative 8R over 3, where R is the number of rounds. Now plugging in some values, we get 10 to the negative 8, or basically 1 over 100 million security when we use 10 rounds, sort of what AES does. And if we increase it up to 24 rounds, we get much better security. Now, there are some, what is the setting? We prove it for random S boxes, but because the S boxes are so small, we can sort of hardwire it. And we have this constraint on the linear P box. Basically, it cannot have any zeros. The Wichs matrix and its inverse have no zeros. So what is this? This is almost the real AES. And why is it of substance? Again, is because we get precise, quantitative, round-dependent security, and there is nothing unspecified here. Now,
Harish,
yeah.
Is this like aligned with what we know about AES in terms of the security that we get?
Yes, I'll cover it in just a few slides. So what do we actually know in traditional cryptography? So what do we actually know? That's an amazing segue into my next talk. Next part of the talk is how does the small box thing that we're throwing it in, how does it actually contrast with something that we know in traditional cryptography, which we call it the big box? We typically have this hard object, which is basically this box, which is at least security parameter big, and it's from a whole bunch of assumptions. You can have the big box as or an idealized model. And the issue is that it sort of does not capture real-world symmetric crypto because it's often too coarse and abstracts away the most interesting parts. I mean, at least what we consider the most interesting parts. And it does not really give you a picture about how to build it from something really small, which is basically an 8-bit S box. Okay, so what does traditional crypto or big box crypto give us in terms of SPN analysis? So the idea is basically replace the entire SPN structure with one big permutation pi, right? And the thing is now it's no longer SPN. Okay, we have a solution. Let's just rename it, and we call it the key alternating cipher or KAC. And typical security analysis is we prove the PRP security in the big box framework of a random permutation model. But immediately we get that even one round is enough. That's the famous Evan Mansour cipher. And which brings us to the question, is it enough to bring theory to practice? And the answer is that it does not appear to be, right? And why is that? So basically, if we look at what we are selling, on one hand, we have this SPN, which we analyze in small box security. We say it's 2 to the negative 8R over 3 security in R rounds, right? Which is very precise, clear. But then on the other hand, I mean, yes, so they high-five, they celebrate, the practitioners are really happy. But on the other hand, you basically have something like the Evan Mansour cipher, which is basically a whole bunch of question marks because you don't know what is the security in terms of the number of rounds. And you also don't really know how to instantiate this pi. So why is something like the SPN better choice of pi as opposed to something else? Or and any SPN is never actually ideal, right? Because there's always this huge gap between what is ideal and what is real. And when we give it to the practitioners, there's a bit of a head scratching, right? So this is the state and so basically we have these two frameworks, the small box and the big box, and the goal is, and basically what we get is meaningful security in as a function of rounds. And we also get nothing unspecified, everything is clearly specified, but obviously there's this big conjecture part. So what is this small box? Let's open it up slightly. So it's mixture of hardness proofs and hardness conjectures. So the first step is traditional hard or impressive reduced round proof, which we do it in the big box work. And it's just conceptually harder than normal proofs. There's some kind of domain extension. And on the other hand, the second step is hardness amplification step, which is possibly provable. Again, we do it in the big box world. And what the idea is that you will amplify the result for multiple rounds under the same runtime of the adversary. And it could be unconditional with independent keys. The results of Maurer et al. gives us that little bit of theory grounding to make this result provable. So we have, oh, my animation is slightly glitching. The third step, or the conjecture part, which appears to be a really crazy assumption, but is almost needed to make it, but it is needed. You need something crazy to make it go through. So that's the part, the big to small conjecture. And it's the only conjecture part of the framework. So we use extensive theory, we use extensive proofs, and then make this jump to actually get meaningful results. So what is the big to small philosophy? We present natural construction that makes sense for any n. We typically have t comma epsilon of n security, but only if n is some a log t or something. And clearly the proof breaks down if n is too small, but there's no matching attack actually. So just the proof breaks through. So we basically say, okay, the conjecture, the philosophy is that epsilon of n is still meaningful and still great even for n is equal to constant. So the conjecture or heuristics is basically this in a distilled format. Is despite supporting proof breaking down, we get still security even when n is constant. And there are many options for this choice of epsilon prime of n and epsilon of n based on our definition of approximately and the definition of constant. The most aggressive version would be something like, okay, epsilon prime of n is epsilon of n plus something that accounts for the brute force attack. So if an attacker can run in time t, what is the security loss when we have brute force? Now, is this sound? The hope is yes, but we need to be careful because it's not true always. It falls for direct product where in place of cascade. So with the if we can do, if we are given s of x1, so on and so forth, s of xr, and the security is t comma 2 to the negative rn over 2, but it is trivially breakable if n is equal to constant. But we don't know any attack if we cascade or XOR. Where the operation sort of destroys the individual instances. So general attack on cascade might also attack AES, right? Because AES is basically this cascading SPN structure over and over again. And interestingly, what we can do is we can take our framework, our recipe, and follow the same thing. And we end up with a stream cipher or a PRG, which we can independently prove secure and with something that's from the big box world. Under a variant of the LPN assumption. There's no behind the scenes, there is no fudging of anything, there's no conjecture part, it's something that's direct. So we basically have this collision between big box and small box, which is interesting, and clearly more validation is needed. But the bigger question is, why is this better than just saying AES is secure? Small box crypto has a really large provable component. In fact, quite.
You should wrap up, okay?
Yeah, I'm almost done. I'm just going to the so what we get is everything is precise and we get quantitative bounds in a very systematic way. Yes, there is a conjecture, which is syntactically natural and we prove it for any n. So the bigger picture, almost done. We need theory of hardness from small components. Conventional models or assumptions fail. So the hope is we have this new thing, which is the big to small conjecture, which is sort of friendly to small box cryptography. We can think of it as one-way function. So what is a new philosophy for design? We are stuck in the thing. We need the worm. We don't know what to do. So we go to the big box world. We solve everything that's possible in the big box world, but then we come back to the small box, but we don't really come back empty-handed. We come back with all the proofs that we have done in the big box. And clearly a lot of work remains, but hopefully this is the starting step to this unlocking this whole world of research called the small box crypto. Thank you for your time.
Okay, thank you very much, Harish. Thank you for those amazing animations. We're slightly over time. If somebody has a brief question, he can ask now when the next speaker prepares. So this is Neekon, right?
Yep, that's me.
Okay, so you can share your screen. Okay, and now we're going to hear about how to get average case NP hardness.
All right. Hi, everyone. So I'll be presenting average case hardness of NP and pH from worst case fine-grained assumptions. And this is joint work with Lijie Chen and Shuichi Hirahara. So we're all familiar with the P versus NP question, but how does it relate to cryptography? So if P equals NP, then there are fast algorithms for many hard problems. But sadly, it also means that there's no cryptography. On the other hand, if P does not equal NP, then there are no worst case fast algorithms for NP complete problems. But what does that say about cryptography or even average case hardness? It turns out that we don't really know, and it remains an open question. But to get a better understanding of what possible worlds we could be living in, Impagliazzo devised 5 possible worlds relating to the existence of algorithms for hard problems and cryptography. For example, if we look at the hardness column here, these green implications upwards are straightforward. If there is public key crypto, then one-way functions exist. And if one-way functions exist, then NP is hard on average, and so on. But on the other hand, implications in the other direction are unknown. And for example, if we look at the second yellow arrow, if this implication did hold, that would mean that NP would be hard on average if and only if P does not equal NP. And what this means is that the world heuristica in the second row here could not exist. So each yellow arrow corresponds to eliminating a possible world. And identifying which world we live in is a central question in complexity theory and theoretical cryptography. But unfortunately, there are many barriers in the way of proving these yellow arrows, and any proof of a yellow arrow here has to simultaneously overcome all of the barriers in its way. Okay, let's give some quick complexity background to define some notation.
And we have also some new worlds like Obfuscation.
Yes, very true. Definitely. We'll mainly deal with heuristics here, but yes, there's lots of wild worlds out there in crypto. So for some complexity background, we have P and NP, just defined in the usual way. We will also use UP, standing for unambiguous polynomial time. Same definition of P. Inputs have exactly different from NP, but every instance has 0 witnesses, which is just like NP. Okay. Sigma 2P and ITP are defined as usual as classes within the polynomial hierarchy, which is also defined as usual, but these classes aren't familiar, then don't know much about it. I'll define some average key quotient, going to be crucial. So I'm going to define average key here to be the set of all.
Neekon, I think you have an internet problem. Okay, I think we lost him. Let's give him a minute to try to return. If not, we'll do. Okay, I see him back.
Sorry
okay,
about
Neekon,
that.
Yeah, you had some internet issues.
Oh, no. Okay.
So please, yeah, so just reshare your screen and maybe jump back like 7 seconds. Like, okay, yeah, you defined P and NP. That's fine. And yeah, take it from here.
Sure. So UP stands for unambiguous polynomial time. It's the same definition as NP, except that all inputs are going to have at most 1 witness, meaning that every yes instance must have exactly 1 witness, which is different than NP. But every no instance has 0 witnesses, just like NP. Sigma 2P and pi 2P are going to be defined as usual as classes within the polynomial hierarchy, which is also defined as usual. But if you haven't seen these complexity classes before, then don't worry too much about it. But now let me define some average case notions, which are going to be crucial for us. So I'm going to define average P to be the set of all languages L and distributions D, such that there is an algorithm solving L always correctly, but the expected running time of the algorithm when taking inputs according to distribution D is polynomial. And I want to emphasize that when I say expected polynomial time here, I mean the expectation taken over inputs according to distribution D and not internal randomness. And that's what makes this an average case notion. Similarly, we'll define distributional curly C to be the set of all languages L and C and distributions D that are polynomial time sampleable. And this just allows us to syntactically say that some class of languages and reasonable distributions have average case algorithms. Recently, Hirahara had a breakthrough work in giving evidence towards eliminating heuristica, the world where NP is hard on the worst case, yet easy on average. Specifically, he showed that if this class UP has this worst case complexity assumption that it can't be solved in time 2 to the O of n over log n, then distributional NP is not contained in average P, or equivalently, NP is hard on average. He showed a similar result for the polynomial hierarchy, and also one for NP instead of UP, except now this last consequence here means that NP can't be solved in average case polynomial time, where the runtime must also be able to be efficiently estimated for all inputs without having to run the algorithm itself. It turns out that if we look at this first result, for example, 2 of the 3 barriers from before apply for this result, but it was unknown if the relativization barrier also had to be overcome in proving this result. And one can ask, can we do better than this first result? Can we use a weaker worst case complexity assumption to give the same consequence that NP is hard on average? But it turns out that for this question, a new relativization barrier indeed does come up, showing that it might be difficult to directly improve these results. And one crucial thing to point out here is that these results just fall short of the exponential time hypothesis. As a quick reminder, the exponential time hypothesis says that 3-sat on m variables requires 2 to the omega m time, which is a much stronger assumption than p does not equal np. Yet these worst case complexity assumptions considered in the theorem statements are stronger than ETH. And indeed, they're even stronger than the strong exponential time hypothesis, SETH. And the reason why is just due to the way 3-sat instances are encoded as binary strings. Okay, so this begs the question, what is the weakest worst case complexity assumption that implies non-trivial average case hardness? Our answer is that we can get non-trivial average case hardness from the exponential time hypothesis, and even in some sense, much weaker worst case assumptions. Specifically, we show that if UP has a weaker worst case complexity assumption, that it can't be solved in time 2 to the O of root n log n, as opposed to 2 to the O of n over log n, then non-deterministic linear time can't be solved on average in quasi-linear time, this O tilde of n, meaning n times polylog n. We get a similar result for the polynomial hierarchy, but there's one thing I want to especially emphasize here. Previously, it was unknown if even average case hardness of sigma 3p implies average case hardness of sigma 2p. But here we show that not only average case hardness of sigma kp implies average case hardness of sigma 2p, but in fact, even worse case hardness of sigma kp for any k implies average case hardness of sigma 2p. And lastly, with the exponential time hypothesis directly, we get n to the 1 plus epsilon hardness, except that the runtime must also be able to be estimated in time n to the 1 plus epsilon. The main technical contribution that enables these results to go through.
Neekon, you should be wrapping up.
Okay, so the main point is that what enables these results are very efficient pseudo-random generators. So our theorem is that from an average case easiness assumption, we get a PRG that has log m seed length that fools t time distinguishers. Yet the PRG is computable in t times poly m time, which is very little overhead in the case where t is very big. Like there's only a poly m overhead in between the class of distinguishers it fools and the runtime itself. And this efficiency is what enables these results. So just to summarize and give some open questions, we use meta complexity just as Hirahara does, and this allows us to overcome the barriers. And perhaps fine-grained complexity is the right lens to look at this through. And pseudo-randomness is, unsurprisingly, a very powerful tool. And for some open questions, can we do better than 2 to the O of root n log n in this assumption? Is there any barrier? And can we go from fine-grained average case hardness, perhaps all the way to fine-grained crypto? All right, thanks so much. That's all.
Okay, thank you very much, Neekon. That was great. I think these are great progresses on this question. We don't have time for questions, so we'll just move on to Luowen, who will tell us if we are sitting close to him or far away from him. Okay. So can you share your screen?
Can you see?
Okay, yeah, great, you're on.
Okay, yeah, thank you very much for the introduction. So yeah, I will be talking about this recent joint work with Jiahui Liu and Qipeng Liu from UT Austin and Simons Institute. And as Eylon has kindly introduced, our work will be about beating classical impossibility of position verification. So just to tell you the setting of the work, so what is the task of position verification? So just think of you have an astronaut and he is going away for some space exploration task, and you want to verify that his position is indeed at the correct position. So for this talk, let's think about this as a prover who wants to prove his position to the verifier. So here's a verifier. So the main thing or the main technique you can do is what is called distance bounding, which is that if you send a message to the prover and expect he to respond instantaneously, and if you time the this response time, then you will be able to estimate the distance, in particular, for example, in this example, you will be certified that he is within this circle from your location. So in order to get a better estimate, what you can do is to simply repeat this process with a bunch of other verifiers and then triangulate the prover like so. Unfortunately, this very simple technique or idea is actually insecure if you consider multiple adversaries that that are colluding and want to jointly convince you that they are in an incorrect position. So in this example, these two adversaries are able to convince the prover that they're in the middle, but in reality, both of them are very far away from the middle with the naive protocol that I just described. So what is the state of the art for position verification? So this task was first formalized by Chandran, Goyal, Moriarty, and Ostrowski in 2009. And there they also show that in general, if you have a purely classical protocol, then a bunch of colluding adversaries can always attack your protocol. Yeah, and at the same time, they also give another classical protocol that is secure against bounded storage adversaries. In particular, they assume some hardware assumption on the capabilities of the adversary. And prior to our work, all the other position verification protocols are quantum. In particular, they use quantum communication. And one very important property that they use is the no cloning property of quantum communication. And therefore, this begs the question, which is that, can we still get around the classical impossibility with only classical communication? And this brings me to the our main result, which is that we show that assuming that learning with errors, which is a widely used cryptographic assumption, is hard against quantum computers, then we show how to get classically verifiable position verification against unentangled quantum adversaries. So what do I mean by classically verifiable? It means that all of the verifiers only have classical capabilities. In particular, this also implies that the communication of the protocol is purely classical. So one natural question is, can we do better than what we achieve here? And we also prove that for a classically verifiable position verification, you will have to use a quantum prover in order to not hit the classical impossibility. And at the same time, we also show that you have to assume some computational assumptions. In particular, we show that any such protocols implies the proof of quantumness for a single prover. And the nice thing about our construction is that it is actually very simple and a lot of the existing ideas from quantum position verification literature can be more or less naturally ported over to our protocol without much trouble. And this is brings me to the second part of our result, which is that we can strengthen our base protocol with stronger security guarantees if we assume stronger hardness assumption. So in the first part, if we assume LWE is sub-exponentially hard, then using some ideas from the quantum position verification literature, we get a protocol that is provably secure against adversaries with bounded entanglement, or if you know the entanglement bound a priori. Of course, this is not very ideal, but if you want unbounded entanglement, then we also show how to combine our protocol with Unruh's protocol to get a protocol that is secure against unbounded entanglement. But the security is only proven in the quantum random oracle model, which is also a very standard quantum cryptographic ideal model. So finally, we also show that for the standard model construction, so everything except the last one, we also show that if you share enough entanglement, then you can, of course, that's enough polynomial amount of entanglement, you can also attack our protocol efficiently. So it remains an open question whether you can get a standard model provably secure position verification. And this more or less matches the state of art in the quantum position verifications in terms of entanglement. In particular, it is also not known whether there is a standard model entanglement, unbounded entanglement secure protocol in a standard model. Okay, so instead of telling you how we achieve this, instead I want to motivate why having classical communication actually could matter for practical purposes beyond the theoretical interest. And
can I ask a question?
Yes.
Do you allow shared randomness like for free, and you only bound here the entanglement?
Yes. Anything classical shared randomness is allowed. You can share any polynomial amount of shared randomness.
Okay, thanks.
The only thing is entanglement. And this is similar to what happens for quantum position verifications as well. Okay, so going back to the practical advantages of our protocol. So the main disadvantage, which is like the dual of advantage of classical communication. So the disadvantage of quantum communication is that in the context of position verification, the only model of or the only means of communication that makes sense is wireless communication or free space communication, because it wouldn't make sense to have a position verification protocol with wire communication. And one inherent property of wireless communication is that its loss is very high. And why is this a problem? Well, actually, back in 2015, Qian's diopsies have shown that a lot of non-quantum position verification protocols break down if the loss of the communication is high. And therefore, it's ongoing research to construct loss-tolerant position verification protocols. And as far as we are concerned, there are only two works that construct fully loss-tolerant position verifications, which means that it will give you some meaningful guarantee no matter how high the loss is, as long as it's bounded away from one, or noticeably bounded away from one. But unfortunately, the security for these protocols are only proven against unentangled adversaries. But if you look back at what happens for classical communication, well, you can just repeat the classical communication at no cost to the security. And therefore, a corollary of our work is that we actually get full loss tolerance even against entangled adversaries, which we believe is not something that is known before. Yeah, so there are also other practical advantages, like if you are sending classical communication, you don't need a laser, whereas for QKD, people have been using a laser to do free space QKD. And it is also easier for composition. So to conclude my talk, so there are a few interesting open questions in this area. One thing I will mention is that our protocol requires the prover to have some quantum memory, and our security proof relies on a notion of computational unclonability. So one very nice question is that whether we can remove quantum memory from the prover, because this seems possible, but we don't know how. So that concludes my talk. Thank you very much.
Okay, thank you very much. That was really cool, especially the lasers. Yeah, James, you can go ahead and share your screen. Okay, so James is gonna tell us how to use circuits that always output 0. The stage is yours.
Great, thank you. Yeah, so I'll be discussing this work indistinguishability obfuscation of null quantum circuits and applications, and this is joint with Giulia Malavolta. All right, so first a little bit of background on classical obfuscation. So an obfuscator is a compiler that takes a computer program P and outputs an obfuscated program. And the point of the obfuscator is to scramble the program in order to hide its implementation details while maintaining the functionality, okay? And so the security property, at least for this notion of indistinguishability obfuscation, says that for any two functionally equivalent programs, their obfuscations should be computationally indistinguishable. And this has been a really hot topic in cryptography over the last decade, partly just because it has so many applications. It's been called the central hub of cryptography. It implies, a bunch of crazy things: fully homomorphic encryption, functional encryption, public key quantum money, and the list goes on and on. And so there's been a lot of work in, the classical cryptography on building stuff from IO. There's also been a lot of work on building IO itself. Okay, and so after, again, decades of work, we have right now a nice construction from well understood assumptions that include bilinear maps. So we also have a very active line of research that's also providing post-quantum candidates that don't rely on bilinear maps. So this is still an active area of research. So this talk, though, is about the notion of quantum obfuscation, which has been, much less well studied, but it asks the simple extension of this question in the classical setting, right? So if you have a quantum circuit or, a quantum computer program, can we also compile it with an obfuscator into an obfuscated version, right? And so just to mention, there's a few works that have dealt with this notion of quantum obfuscation, a few on, defining things in the quantum setting, extending some classical impossibilities to the quantum setting. But in terms of applications and constructions, much less is known than in the classical setting. So in terms of applications, other than IO itself, I am pretty much only aware of this work that shows that quantum IO implies this notion of witness encryption for QMA, which I'll actually touch on a little bit later. And in terms of constructions, there's a couple of works that have studied, which classes of quantum circuits can we perfectly obfuscate. So these will necessarily be for pretty limited circuit classes. We can't really hope to perfectly obfuscate all quantum circuits. And there's another recent work. This recent work also shows that we can do quantum IO for circuits that consist of only Clifford gates plus very few non-Clifford gates. So actually logarithmically many non-Clifford gates. So this gives, and this is from classical IO. So this gives a class of circuits that can be IO'd, but it's quite limited. All right, so in particular, this question remains open. Is it possible to realize indistinguishability obfuscation for general quantum circuits? And by open, I mean we still don't even know if any candidate constructions or heuristic constructions. In the classical setting, we've known candidates for about a decade now, and the initial candidates kind of sparked a huge line of research on this question. In the quantum setting, we don't even have yet a candidate for obfuscating all circuits. Okay. So our work is basically attempts to address both aspects of quantum obfuscation, so both applications and constructions. So I'll first present our first result, which is our construction. So assuming the quantum hardness of learning with errors, a standard post-quantum hardness assumption, along with virtual black box obfuscation for classical circuits, we show that there exists an obfuscator that operates on quantum circuits, okay, with correctness. So it basically, for every quantum circuit, it maintains functionality. And I should mention these are quantum circuits with classical output. So it maintains functionality. For security, we ask for any pair of quantum circuits Q1 and Q2, such that both Q1 and Q2 output 0 with overwhelming probability on every input, basically that they're both null circuits, their obfuscation should be computationally indistinguishable. Okay, so basically we're asking for functionality preservation for all circuits, but security only for pairs of null circuits. And this is extending this classical notion of null IO that has been studied before. Okay, and yeah, before moving on, I should just say a few words about this assumption. So we know actually that VBB obfuscation is impossible in general. There exists like contrived circuits that just can't be VBB obfuscated. But what you could do is say, well, you know, we actually use the notion of VBB to get our security proof to work, but you could just plug in an indistinguishability obfuscator in place of this VBB obfuscation in the actual construction and still conjecture that the that the resulting quantum obfuscator is secure. So that's kind of similar to what people do with hash functions in the random oracle model. So it gives a heuristic construction. We also show that we can replace this assumption with classical IO plus something that we define called dual mode, classical verification of quantum computation in the paper. Unfortunately, this is also only known heuristically at the moment. So the takeaway right now is that what we construct is a candidate or heuristic construction of IO for a large class of circuits, namely all null circuits. Okay. And then the next part of our results are on applications. So, we construct this object, and actually our obfuscated circuit can be classically described. And first we show that this still implies witness encryption for QMA, okay, with a classical ciphertext. And then we go on to show that this witness encryption primitive for QMA is actually very powerful and implies a lot of things. So, for example, this allows us to give the first candidate construction of non-interactive zero knowledge for QMA, okay, which has not been known before. Another example is we give the first, so attribute-based encryption is a notion of fine-grained public encryption that has been pretty well studied in the classical setting, and we give the first construction for ABE for quantum predicates, for predicates in BQP, okay. And I'll have to refer you to the paper for all of these implications. I just want to spend a couple minutes on this actual construction of quantum null IO, which is actually pretty simple. So we basically use two tools. One is a two-message blind classical verification of quantum computation protocol, CVQC. So this is between a quantum prover and a classical verifier. It's just a two-message protocol where the verifier has a circuit Q they want evaluated, the prover has an input, the prover provides a proof, and then the verifier outputs Q of X, which is equal to Y. Okay, so this is just a two-message classical communication CVQC protocol. We need to assume that it satisfies both blindness and soundness. And we can get this by just combining recent work on CVQC with a quantum FHE scheme. Okay. And then we also need an obfuscator for classical circuits. But given these, the construction is quite simple. So to obfuscate a circuit Q, you run the verifier generation algorithm to get public parameters corresponding to Q, which is the message sent to the prover. But then you just simply classically obfuscate the verifier's output circuit. Okay, so the quantum obfuscation of Q are these public parameters, along with a classical obfuscation of this output. And then to evaluate, you run the prover to produce the proof, plug it into this classical obfuscation to get the result Y. So quickly, why is this plausibly secure? Well, what we can show is that if Q is a null circuit, then this classical oracle, this obfuscation, can basically be replaced with the all zeros oracle. And we can show that any adversary that distinguishes these oracles, even if they have superposition access to these oracles, can be used to break the soundness of CVQC. So we can safely replace this with the zeros oracle. And at this point, we can hide Q we can argue that the public parameters hide Q due to the blindness of CVQC. And so this is established that this entire obfuscation here is, basically hiding Q. Okay. Yeah, so that's all I wanted to say about the construction. You can see the paper for more details. Quickly wrapping up with a couple of open questions suggested by this work. One natural one is, can we extend our construction to get I/O for all quantum circuits, not just null circuits? And if you try to directly extend our approach, you run into an issue, which is basically requiring that the underlying CVQC scheme that we use satisfy something called reusable soundness and blindness, meaning that it's secure even if the prover can query the verifier over and over again. It turns out that known CVQC protocols, as we show, are actually not reusable, and we show attacks on them. So this is a nice open question, is if we can come up with such reusable CVQC schemes and extend our approach to obfuscating all quantum circuits. And then another one is just, can we get any, our null IO or even any of our implications from just say IO for classical circuits? So can we remove the VBB assumption from our proofs? And so that's all I wanted to say. So thanks for listening.
Okay, thanks, James. Thank you very much. If there's any questions, people are all welcome to ask. I'll just say in the meantime that, so you use VBB for this verifier circuit, right, at the end? So it could be that you can come up with a protocol with where this verifier is like extremely simple. So maybe we actually do have VBB for.
Right. Yeah, you're right. If you look at actually what that verification algorithm is doing, it is pretty simple. Like the operations are actually simple, but yeah, it is unclear how to actually instantiate that from VBB. So we've looked into that a little bit. Yeah.
But we do have VBB for like a lot of classes of circuits, which are simple, and also maybe this verifier escapes the impossibility results at least. So, so like you do have a candidate. Okay, thanks, James. That was cool. I think obfuscation will be like one of the main things in the next 10 years, 20 years when it becomes like very practical. Okay, that's the end of our session. There's another session that started like 2 minutes ago in room B. You're all welcome to join. Thank you so much, and see you in the other sessions.